So make sure you read Dingles Topic9 stuff. I'd go through that whole packet. There's some stuff I'll tell you tomorrow whether or not we're going to get to it or not. Something called Born-Haber cycles. But for now, don't worry too much about Born-Haber cycles if you get ahead on the reading. But for sure, at a very minimum, look at page 1 there at the beginning, the definitions. You want to make sure you're familiar with all those definitions. Many of them we already had, so like systems, surroundings, we had those, we had drawings, you should be able to draw it, describe what it is. Open system, closed system, so like in lab, when we did the calorimetry lab, we had an open system because we didn't have a cover, and all our heat and a lot of other things could get out of the reaction. Closed system is where you totally close off the system from the surroundings. An isolated system, nothing can be transferred, as it said. State functions, so this is new, you might want to star that one, or the last three for that matter. So state functions says there, state functions are those that depend only upon the initial and the final state of a substance. So examples are delta H, delta S, and delta G, everything we've been covering. In other words, you might want to add this, it doesn't matter how you get from one point to the other. It's kind of like climbing a mountain. A state function doesn't matter how you get to the top. It's the beginning and the end that matters. Okay? Many different paths to get to it, but it's the beginning and the end that matters. Specifically the end. And then an extensive property, you might see this in multiple choice. So extensive, watch for that. It says property that depends on the amount of substance present, such as mass. If you're measuring the mass of something, the more stuff you have there, the more mass it's going to have. That's extensive. And then intensive property, the example there is one that does not depend on how much stuff you have or the amount of substance you have. So boiling point, whether you have a little 50 ml beaker of water or a whole swimming pool of water, the boiling point of water is still 100 degrees Celsius at standard conditions, or at 1 atmosphere, I should say at least. Okay? So make sure you know the difference between those two. And then there's some other things in the packet that I'll kind of go over here. You'll see them when you go and read through. There's something called bond enthalpy. I'm going to write these ones out. So bond enthalpy, it's in the packet. My definition is going to be the amount of energy required to break. So we talked about this before. If you're breaking bonds, are you putting energy into it? Is energy being absorbed or is energy being released? If you're breaking bonds. So I always think of it this way. So here's a bond. Just put your hands in front of you in class if you have to on a test. What does it take to get your hands apart? It takes somebody else to come and slash them apart. That takes energy, or that requires energy. So breaking bonds requires energy, or you have to put it in, so I'm going to write positive there. So energy required to break a bond, and or, depending on how it's being talked about in a problem or a situation, so and or the amount of energy released when a bond is formed. So if energy is released, it's being given off, it's going to be negative. For whatever reason, it works for me and it's worked for many others. Maybe it will work for you, maybe it won't. But the two cars crashing example, if two cars crash into one another, a lot of times they get connected together, they get mangled up in the front. You formed a bond there. So when they crashed, the bond was formed. Was energy released or absorbed? It was released. I just, in my head, think about stuff flying all over the place. There's all kinds of energy being released in that situation. If you don't, that doesn't work for you, so be it. But some people it does. So. And then you can have delta H, a simple equation here. Delta H of bond energy equals the sum of the energy, this is basically the bonds broken, minus the sum of the energy of the bonds formed. So that sigma sign, remember, means sum. And a lot of times this bond's broken. That has a special term. It's called bond dissociation energy. bonds formed here part is sometimes called bond, I call it my own, you don't see it in a textbook often, but bond formation energy. Or, it's a true technical term, it's called lattice energy. So lattice energy. Bonds form, a lot of times if you have a crystal structure, it's called a crystal lattice, where the atoms are all hooked together. That's what that's referring to. So that's important. That'll potentially come up in today's homework. And then there's energy diagrams, they're called. You will see these more than likely on the quiz, which is now on Friday. You'll see them on the final exam. You'll see them on the test, maybe before we go on break, but probably after. We'll see where we're at. See it on the national exam. And they look something like this, where it's just a graph. So you have an X and a Y axis. And usually on the X axis is what they term reaction progress. Sometimes they don't even label the X axis, but it's time basically. You can think of it as time. I'm going to call it time here in quotes. And then on the Y axis, we're looking at the energy. Often it's the potential energy, chemical potential energy, so I'm going to say PE. Okay. And what these look like often is you have a certain energy. So we're going to say our graph is starting in this direction, where you have A bonded to A, just some element, doesn't matter what it is. And it's going to enter into a reaction, reacting with B. What happens is, for a reaction to occur, it's just like lighting a match. You have to put a little bit of energy in. So what's going to happen to our graph here if you have to put energy in? It's going to go up or down? It's going to go up. So it'll rise up to whatever level. We're not dealing with numbers here. And at this point, so the reaction started and you reach a peak here where you might have A connected to A to connected to B. So it's reacting with B, we're saying. And that's called an intermediate product. You'll see that in kinetics when we talk about kinetics in our next chapter, I believe it is. And then that basically falls apart, you get your new product. So that's a high energy intermediate. If you could maybe add that in, it might be good. It's going to come up later. And then you go down to a certain energy level here. Okay. So at the end, you end up with your new product. And this new product, I'm just going to say, is AB plus A. All right. So you have one A left over. And then with this, you look for 2 points. I always look for the beginning and the ending, and then go right to the beginning here. You'll see on the next one. You can draw a dashed line. This usually is not drawn in for you. Okay? But draw on that dashed line, it'll help with something here. And what that dashed line means is there's something called activation energy, or energy of activation. That's the energy it takes to get the reaction going. So like lighting a match, you have to strike a match, you have to give it energy. The friction is giving it heat energy. So this area right here, from there down to here, and I'm going to give it a symbol in the middle. I'm going to call it AE. That stands for activation energy. But basically that area right in there, underneath that pump, is the activation energy. So that can be abbreviated AE. Or, because you might see it the other way, I mean it's simple, but it could throw you off. It's energy of activation. Same thing, but I've had people freak out when they've seen this instead. So it might be EA, energy of activation. And then also here, in this area, assuming our graph went way over, that'd be fine. This area is our delta H, our change in enthalpy. Or you can think of it as energy. And what you have to be able to figure out is heat being released or is heat being absorbed by this reaction? Overall, from beginning to end. Not this part in the middle necessarily, that's just an intermediate process. That's necessary, you don't see it really in there. So from beginning to end, was energy released or absorbed? It was released. So you have a energy of whatever, you could give it some arbitrary number, 4 there, an energy of 2 there, kilojoules, whatever it might be, calories. But the big thing is that you can see it was released. So is this going to be positive or negative on this? It's going to be a negative, okay? So you have to be able to plug in this and say, oh, it's a negative delta H, and then you also have to be able to say, well, that's exothermic then. Okay, so that one's very common. I've had it on quizzes and tests before. Maybe Friday will see it, where it'll say draw an energy diagram showing an exothermic reaction, and you draw all this in. Or draw an energy diagram showing an endothermic. So if we draw an endothermic, or try to draw an endothermic, we're going to have reaction progress here, or time. Your energy, a lot of times you might just see E here on the left. Again, I can't tell you exactly what they're going to have on the national exam. There's so many different variations, you just have to kind of recognize things. That's what they're trying to get to. So potential energy there. So for endothermic, how should it look compared to the exothermic one? Again, it's the beginning and the end that really matter. Think about the beginning and the end. What's that? The ending point should be higher than the beginning, and that's the easiest way to think about these on a test situation. So the ending point should be higher. So I'm going to start my beginning point a little bit lower so that I can achieve that. So I'm going to have, if I can draw correctly here, you have reaction starting, then you add some energy so it can happen. You get over that peak of activation energy, and then you can end it anywhere. So I'm going to go right here. Okay. So now, so I said draw that dashed line. Think about this too. Always draw the dashed line from your beginning straight line here, where the energy is constant until you add it. So I'm going to add in my energy, or my dotted line here. And then you can get a lot of information from that. So where is our activation energy? That's from beginning, what you start with, to your highest point. So it's from here to here. So that's our EA, or AE. Where's our delta H? From the ending point to wherever the beginning point was in terms of that baseline there. So this is our delta H. And in this case, the energy at the end is higher than at the beginning of the reaction. So energy was absorbed. So you say a positive delta H, and then it would be endothermic. So I'd go through drawing those a couple times. Make sure you're set with those for Friday. Like I say, you're more than likely to see. If you don't see them Friday, you're pretty well set that you're going to see them on the test, whenever that is. Okay. So I got one more example here for today, and we'll get you going on your homework. So the example here is going to be, I'm going to write it down, write it like a problem. So I'm going to say calculate the enthalpy change for the following reaction. Using a lot of times it'll say using the table of bond energies. So I'm going to write it like that. Sometimes it'll give them to you right in the problem. So I'm going to give you some here. So that'll be my note. So I'm going to say an O-O bond. So we're going to need it. Equals 495 kilojoules mole inverse. So kilojoules per mole. I'm going to say the C-double-O bond that you're going to see here coming up equals, so this is equals, not a double bond on that after here. So C-double bond O equals, it's going to be 799. And actually, I'm going to give you all of them in the end here. Okay. So here's the reaction. So we have CH4 plus 2O2, so it's combustion of methane, goes to CO2 plus 2H2O. And the first thing you have to be able to do with a problem like this is to draw out the Lewis structure of everything that's in the problem. So go ahead and draw out those 4 Lewis structures. It doesn't have to be 3D, it doesn't have to be fancy, it might help. Maybe you're just used to drawing in 3D, so I want you to draw those first before we do anything else. Try to draw the CH4, the O2. Basically, you're using stuff from the last chapters on this now. I'll say, especially getting like the O2, you want to make sure you can get O2's Lewis structure on your own. Haven't done that in a while, something like that. It's simple, but CO2 you almost have memorized probably. Pick on a few people here for the structures. So for CH4, it's a structure for CH4. What shape? Tetrahedral. So what goes in the middle? C, and where does all the hydrogens go? All the way around it, so that one's easy. If you want to draw in 3D, remember to bend down those sides. Might even be worth putting tetrahedral underneath there. It could help you later on. How about O2? What shape? All it can be is linear. What kind of bond between it? It's a double bond it ends up being. Any lone pair of electrons? Where do lone pair electrons go? Where? 2 on each oxygen it ends up being. So if you can't get these, you're not going to be able to get the problem is the point here. CO2, should almost have that one memorized. We've done that one so many times. Something like that. Water you should have pretty much memorized. Looks something like this. Okay. So now turn to page 5 in that note packet. So you got an example of what one of these tables looks like. And all the way up until page 5, this packet deals with Hess's law, so you got more Hess's law practice today once we get to the homework. So the BET in this table, he says it's called bond energy term. That must be an English thing. I don't know. I never heard it called that before this, but it's just bond energy. So what you need to do is look for the bonds, and you also have to watch for this. So on this side, On the reactant side, are bonds being formed or bonds being broken? On the reactant side. Use common sense. You're going to rearrange these atoms to put them together like this. So what do you have to do to the bonds over on the left side? Break them. So on the left side here, I'm just going to write, just because it could help in a multiple choice later on, bonds are going to be broken. And then on the right side, bonds are going to be formed. And that's the very, very basics of chemistry here, rearranging atoms. Okay? So what you need to do is look at, on this, the CH4, the first molecule here, look in that table and look for a C single bond H and see what that value is. Okay? What's that? 412. So for CH, it's 412. 412, what's the unit? Kilojoules per mole, watch out for that. Well, how many moles of CH bonds are right here? There's 4. There's 1 mole of CH4 according to the coefficient. But within the CH4, there's 4 different bonds. So there's 4 moles worth of bonds here. So you go 4 moles times the 412 kilojoules per mole. So your moles would be gone then. Plus your oxygen here. I'm just going to add it up on the bonds broken side here. So the oxygen, what's an O double bond O? O double bond, and there's O single bond probably. Where'd you get that from? I gave it to you because it's not in their table. So how many O double bond O's are there? There's 2. So here's 1 times 2 is 2. So there's 2 moles of the double bond O times the 495 kilojoules per mole, so that the mole will cancel. So you'll get a value here. Okay? So this value is 2,638 kilojoules worth of energy. Okay? And then you're going to go minus. Okay? It's bonds broken minus bonds formed. And you could also, thinking about this, if you forget, is it bonds broken minus bonds formed, or products minus reactants, because it's a little bit different here. If you think products minus reactants, you're going to get it wrong in the end. Think more in terms of energy. If you're breaking bonds, are you putting energy in, or is energy being released? Putting energy in, so these would be positive. And in here, bonds forming, energy is released, these would be negative. And then you just add the 2 halves, the 2 parts together, instead of trying to remember this equation. So that might be a better way to go. I'm going to continue the way we started here. So now we have C double bond O. So how many C double bond O's are here? There's 2 moles worth, because it's 1 times the 2 here. So we have 2 moles times, what's the value of C double bond O? That's, I gave you right there, 799 kilojoules per mole. So that mole would cancel out. Plus the H2O. How many? So there's OH or HO. I don't know how it's going to be listed in the table, but look for that bond. Yep, it's OH that's 463. How many OH bonds are here? There's 4. So there's 1, there's 2, times the 2 is 4. So you got 4 moles of the OH times the 463 kilojoules per mole. So now those moles are gone. When you add this up, it's 3,450 kilojoules. So then you would subtract those numbers. Again, if you said, oh, bonds are formed, you put energy in. Here, bonds are breaking, or sorry, bonds are formed on this side. Energy is released, bonds broken, energy is absorbed. If you went that positive and this is negative, and you just added those 2 values together, you get the same answer. Okay? So ignore that the way I'm doing it here, but that might be the better way to go. So this delta H then in the end ends up being negative 812 kilojoules. So if you had this reaction, would that reaction feel cooler or warmer? Feel warmer. It's combustion of methane. That's Bunsen burner reaction right there. So this is exothermic in case they asked. Okay. So now the homework. I'd bring them all the way through Christmas break, probably. So looking at the homework here, I don't know if I'll have to write anything down or not, but the homework, number 1, look at the title, Hess's Law. So Hess's Law is dealing with, there's just one side here. Probably want to do these on a separate sheet of paper, a couple sheets it might take. So in 1, calculate the enthalpy change. So that's delta H. I would underline enthalpy change and write delta H above it. I mean, that's how it might be worded in the AP exam. It's one tiny little tweak to try to throw you off. That's what they do. You're used to seeing calculate delta H. So calculate delta H in the reaction below, given the data below, in kilojoules mole -1, kilojoules per mole. Okay? So that's what you should be ending up with. So all those numbers are kilojoules per mole. So you have a delta HF, that's just delta H of formation of NH3, that means, equals -45. Okay? Delta H formation of NO is positive 91. Those are the numbers from the back of your book. That's appendix 4 type stuff right there. Okay? That's all that is. You have a value for water and you have a value for O2 as well. So how are you going to solve this problem? How are you going to calculate delta H? Products minus reactions. Remember to multiply by the number of moles. So like NH3, you're going to multiply its value by what? 4. What's the unit going to be in the end here? Just kilojoules. Because like the NH3, you got 4 moles times -45.5 kilojoules per mole. The mole is going to cancel out. So watch out for those. You don't want to get little unit things wrong. Looking at number 2, it says consider the formation of ethane. Formation means you're making it. Ethane, in A there, is the C2H6. You might want to write ethane above there. In time, you're going to know how to name those. So given the following data, calculate delta H for the reaction. 2 carbons solid, that's important, plus 3H2 gas, that's important, goes to C2H6 gas, the ethane. You have all those reactions there. What do you do with those reactions? Rearrange them to build that puzzle picture. Okay? So you're trying to build the reaction in A with all those pictures below it. You're going to use them all. So you can multiply, you can reverse, you can divide, you can multiply by fractions, you can do whatever it takes. And you cross things out until you get to that picture. Okay? B, I can leave you with. B, as long as you explain your answer, and it makes sense, you're probably going to be okay. And I'm going to leave you with that for now, I guess.
Mr. Lewis, why did you say this first one was different? Why is it asked the same thing here in the notes?
Say it again?
Like the notes says calculate enthalpy change for reaction.
Yeah, that was bond energy stuff we used in the notes. I don't know if there's one of those in this homework yet or not. I don't think there is. No, there's not. I'm pretty sure you won't see one like the last example in our notes in any homework that remains.
They ask the same thing.
Yeah, it's just a different way of finding it. Let's look at 3 real quick here, now that I'm looking at that. That one's a little bit different than what you've seen before. We've had little parts of this before, but not a whole problem. So number 3, it says calculate the standard enthalpy of formation. So if they say enthalpy of combustion, what does that mean? The heat that is involved when what happens? Combustion. What does combustion mean? Adding oxygen. If they say what is the standard or delta H of formation, what does that mean? What are you doing? Forming something. You're forming a compound from its elements. So you might want to write just a little note about that. Formation, you can circle it in number 3, it's there. The word formation. Formation means forming a compound from its elements. Actually do this. It's forming 1 mole of the compound from its elements, to be exact. So when you balance the equation, and I'll help you on number 3 here. When you balance the equation, the coefficient on the thing you're forming should be what? 1. So you can have fractions for other things. You can have half an O2, for example, if needed, or 3 halves, or whatever. Okay? So with that said, calculate formation of benzene, C6H6, given the following standard enthalpies of combustion. So they got C6H6, carbon, and H2. So let's get the formation of benzene reaction first. This is the picture on our puzzle box. So what are we forming? We're forming benzene. I'm going to do this. I'm going to write my product first. And benzene, you don't have to know what it is yet. C6H6, they tell you. Okay. If you look back to number 2, just as an example, number 2 said consider the formation of ethane. A, given the following data, calculate delta H for that reaction. So they have ethane on the right side, the C2H6, and then they show what it took to make the ethane. It took the 2 things that are in there. So there's hydrogen in this C6H6, so I'm going to write hydrogen. But hydrogen is usually H2 gas, standard conditions. And it's going to take the carbon. So we're going to start with carbon solid. Okay? And in benzene, I'm seeing, look, so what's the physical state on benzene? You have no clue, probably. How do you know? You looked ahead in the problem. So look for hints in problems. So it says liquid ahead in the problem. Okay? So there it is. Now, you want to balance this so that you're left with a 1. The easiest way to do that, and this might work out, nope, it's not going to, is to balance it normal way first. And then we're going to reduce it so that we get to 1. So let's balance this normal way. So what would you put in front of the carbon? 6. What would you put in front of the hydrogen? A 3. So in this case, it comes out to be 1 anyways. But let's say this came out to be a 2. All right? Let's just pretend that came out to be a 2. How would you get this to be a 1? What do you have to do with everything in here? Divide by 2. That would include this. So you would go divided by 2. So it would be 3 halves H2 in the end, and you would leave it. Okay? And they erase that, but that's just what you do. And we had that way a month ago probably now where you had to write reactions like that. Okay? So there's what we're trying to build. And then the data, also other data, it says given the following standard enthalpies of combustion. Look at number 2 again. 2A. There's the picture. And then the reactions, there's 3 reactions. You have 4 C2H6 plus 14 O2. You have C plus O2. You have 2H2 plus O2. All of those are what kind of reactions? Combustions. We're trying to make those same kind of reactions. Except they didn't give them to us nice and neat. We have to make them ourselves. So on number 3, so they have a combustion of C6H6. So we're going to start with that. So I'm going to leave some space here because this is what we're trying to make. So now I'm going to get my combustion of C6H6. What's the physical state again? Liquid. What does combustion mean? Add O2, which is going to be a gas. What is it going to make? Carbon dioxide water. Okay? Doesn't say incomplete or anything like that, so you assume this. So gas. What do you think the physical state on the water might be? Probably liquid. Eventually, some people would say water vapor, but as long as you put liquid on all of them, unless there's some hint in there, but I'm not seeing any hint. And then you have to balance this. What do you leave for last on a combustion? O2. So let's try to balance that. I'm going to try a 6 here. I don't know if this is going to work out. And then I'm going to try a 3 here because I have 6 hydrogens. Now I have 6 hydrogens. But I have 12 oxygens plus 3 more is 15. How would you get 15 here? It'd have to be 7.5. Okay? It'd have to be 7.5. Can you have that? Nope. Okay. So what do you do here? What do you do? Double everything. So it would be a 2, a 2. This would become 12. I guess I'm just going to cross mine out here. And this would be 6. Okay. So I'm going to make a column here now. So the delta H of combustion, I'm just going to do like that. And I'm going to plug it in here. So C6H6, what's the value for that? Negative 3, I'm having a hard time right here. Negative 3,273. What's the unit on that? Kilojoules per mole. So you could write it up here. You could write kilojoules per mole or kilojoules mole -1. Okay, so it's negative 3,273 kilojoules per mole. Anybody see anything wrong with that? What's wrong with that number? So the enthalpy of combustion of C6H6 is 3,273 kilojoules per mole. What's wrong with that number? Yeah, there's 2 moles here though. So what should you do to this number? You got to double that or multiply it by 2. Okay, so you have to double that. You have to double that. Or what else could you do? Instead of doubling this, if you wanted to leave it at negative 3,273, what would you have to do to the reaction? You'd have to have 1 here, 1 mole here. Whoa, this wasn't 7.5. This shouldn't be 2, sorry. I had 7.5, it should be 15. Sorry about that. So this would be 1. This would be 15 halves. Okay? This is how you might see it. You might see it as 7.5. You might see it as, that's probably it. So I'd write 15 halves here. You'd see this as 6. You'd see this as whatever we had before there. It looks like a 2, 3, yeah, because we multiplied by 2. So you could have these numbers instead and negative 3,273 then. Okay? So now what you have to basically do is get the combustion reaction for the carbon. So I'll start you. So it's carbon solid plus what? O2 goes to what? CO2 and what? Nothing. No water here. There's not hydrogen. It's not a hydrocarbon. It's just carbon. Okay, so you got to be careful with that. I'll let you balance that. And the other reaction was H2 plus O2. What is that going to make? H2O. And then I'll let you balance that one and get your delta H values. And then you got to rearrange these equations to get this one. Here's your picture on the box that you're trying to make. By rearranging, multiplying, dividing, doing whatever you have to do. Okay? Where? Right here? C with an S after it for solid. Sorry, I got smudged. Four is very similar to what we were doing in 3.
Wasn't that just 2 right there?
What's that?
That's 3.
This number?
That was 2.
Yeah, it was a 3 originally. We multiplied it
No,
by...
I mean the whole problem. Number.
This is question 3, the stuff, all we did here.
That's okay.